Hi guys, I'm Skylar, and today we're gonna do a sample midterm bomb lab question. Okay, so first things first, we have this a tool at PLT, and that's basically just taking user inputs, right? And the user input goes into REX, which then goes into here, which is the same thing as just doing nothing. It just stays in REX. Sometimes the compiler will do this because we're using a very low level optimization. And you just gotta accept that. Then we're gonna move this value that we inputted into RDI, and then we'll call this function with one parameter. And the reason why we conclude this one parameter is because it seems that we're only using RDI, we're not using RSI. Okay. Now, since the bomb lab, right, we want to avoid this explode. And we can tell from here that if our jump equal resolves, then it'll jump further than it, right? Because it's this. I didn't have this, but basically the stuff after this is like fine. Okay. So that means when I do this compare, it should be equal. That means the value that's returned from this mystery function with the certain parameter RDI that we enter ourselves should return 0x18, which is 24. Okay. Yeah, so that's kind of like how you know, like, you want to put a specific input into this mystery 2, which is like the second phase, I guess, to make sure it returns 24, else you'll explode the bomb. Okay, so that's just a little introduction. Now, to actually, here's some tips. Number one, you want to go line by line, noting register values. Number two, you want to draw the stack. Okay. Yeah. So those are my two main tips. So let's actually, am I using the full? Okay. Yeah, so I like to draw a stack like this. I like to use base 10 because it's just easier in my opinion. And I'll tell you what I mean by that. Basically, I start at 0. And then like at every entry, I just decrement by 8. And this is base 10, so it's not like this is, yeah. Okay, so first things first, what I want to do is I call this function, right? So another important thing is understanding what each thing does. So what does call Q do? Call Q does two things. Number one, it's gonna take this address, in this case 4012A7, and put it into RIP. Function address, and RIP is the program counter, which tells which instructions to execute next. And then the second thing that it does is push the return address onto the stack. So what is the return address here? In this case, it's this, right? Because after you call this function, we should execute this instruction next. So in this case, it would be 40138B. Okay. So now that we have this, let's say we're just drawing our stack, and let's say we just called this function. So as I said, let's say RSP is initially right here before we have this call queue. So let's say our first we do this, and then we, so our RSP is at 0, then we do this call queue. Okay, that means we're gonna push the return address onto the stack. So that means we're gonna push this 38B. Now RSP is here. Why is the RSP here? Okay, so what does push do? So push first decrements RSP. In this case, it'll be by 8, and then places value at RSP. Okay, so that makes sense, right? RSP was here, then we decremented by, then we decremented it by 8, and then we put the value there. Okay. Okay. I'm gonna have this for later. But what does pop Q do? Basically, what push Q does, but in reverse order. So, pops value at RSP into a reg. Then it decrements. Increments. So opposite things in opposite order. Increments RSP. Okay, so these are your fundamentals. Okay, so the first thing we do is we push RBP. What is RBP though? It's basically the frame pointer. In this case, it'll be the frame pointer of the main function or the caller. Okay, we need to store this, so then once we leave Q, we'll go back into the frame of the main function. Okay, so that's this. Now, as you know, remember when we do that, RSP goes here, right? That's how push works. Then we're gonna sub 0x10 from RSP. Remember, 0x10 is actually 16. So now RSP will be here. This is from this instruction. Oops. This is from this instruction. Right here. It was here. And now we subtracted 0x10, which is 16. So now it's here. Okay. Now we're going to move RDI. Remember, RDI was our initial value. Or sorry, the value that we inputted from here. If you remember, we were talking about it earlier. Okay, so we're moving RDI into RBP. What is RBP? I skipped over this for some reason. RBP, remember RSP was -16 before this, right? So RBP is now, RBP took that value from RSP, so now it's -16 here. And then it's -8. So we're moving RDI into -8 plus -16. So that's going to be at -24. So put RDI. Yeah. First called. So first, I'm just gonna say this, like the first parameter of the function, the initial call of the function. Okay. So now that happens. Okay, and then it's a little tricky here. We're gonna compare 1 with this value, as you can see from here. So I'm basically comparing 1 with RDI. Okay, and we're gonna do a jump not equal to C1. Let me write that. So basically, if our parameter value, our parameter value, which is the value that we input, or in this case, since it's a recursive function, just the parameter value. If it's 1, if it's not 1, then we'll jump to here and execute following instructions. Otherwise, if it is 1, what is being done? So it looks like we're moving 1 into EAX. We're moving 1 into EAX. And then we call this function. We jump to DA. What does leave Q do? Okay. So leave Q actually does 2 things. Okay. So leave Q first is gonna move RBP into RSP, and then it's gonna pop RBP. And basically what this is doing your cleanup. After your function is called, we want to go back to our caller frame. Okay, so as you know, or sorry, not as you know, but I'll just explain it right now. So RBP right now, after all this stuff is ran, right, RSP is going to be somewhere, it might do stuff, or it's right now it's right here. And Shit, it looks like we don't move it at all any other places, but we could have moved it here. But the point is that it's here, right? What we want to happen is we want to reset it so that it's so that we have like our current stack for this main function, right? Assuming right, our input was 1, right? Okay, so what we have to do is move RSP back to here. Why? Because we need to use this value to restore this RBP so we can do the same thing again. Let's say if there's a function that called the main function, obviously the main function is the first thing that's ran, but you'll see what I mean when we do the recursive steps. And then what we're gonna do is we're gonna pop RBP, right? So now it's here, right? Our RSP is here. When we pop RBP, that means we're getting our old RBP value and putting it back into RBP, right? Okay, and then now RSP is here, so that we can call return queue. What does return queue do? This is our last little lesson. Return queue does the following. Number 1, places RSP into RIP. Number 2, increments RSP. So now we're going back to the return address, and now RSP is here. So now we're truly right here because this is like the frame of our caller, right? And now we retain our RBP value from here. So now we have like the same thing, and you can see how this scales for recursion. Okay, but that's a little bit abstract since I don't actually have anything here, so it's harder to kind of visualize. So let's just continue. Let's assume our RDI value was not 1, right? Because if it was, that means we would explode our bomb. Right? Because that means we returned a value of 1. Because 1 is in EAX. Okay, so let's say it's like 2, 3, or 4, or 5. I don't know. Maybe something higher. Probably something higher because it has to be higher. One thing to note is like since this is a recursive function, you can tell it's a recursive function because we have a call queue here that calls the same function. We know that when it's not calling a recursive function, we know that it's a base case. So basically, if it's 1, right, that means we return 1. Makes sense? I'll say it again. So if it's 1, we're going to return 1. That's our base case. Okay, now let's kind of analyze this more. What happens if it's not 1? So that means we take this jump because it's not equal. We're going to move this value into REX. Okay, this value is this value right here. We're going to subtract 1 from REX. We're going to move REX into RDI and then call that function. So basically, we're calling this function with the RDI minus 1. So we're calling the same function and getting a return value of RDI minus 1. And then that value that we get from that function, we might make more recursive calls, but eventually gets a value, right? Because eventually we have our base case, and we're decrementing, right? This gets put into EDX. And now we're moving this, which is still the old thing, right, into RIX, and we're going to multiply them together and then leave Q, return Q. So this is basically saying, like given, let's say it's not 1, let's say it's some n, which is not 1, probably higher, like 2 or 3 or 4. Then this is basically saying we're going to return, let's say we're going to return n times this mystery 2 and then n minus 1. Basically, that's what it's saying. Okay? Now, let's say we wanted to validate that because obviously we could be wrong. So we'll go through here. As we see here, we'll just go through here. In this case, we're calling mystery 2. In this case, with the RDA value of the original minus 1. So remember, what does call Q do? First, we're gonna put RIP the function address, which is obviously this function, and we're gonna put the return address onto the stack. What's the return address here? In this case, it's this. So let's do that. 4012D1. And now our RSP is this. Okay. Okay. For convenience, let's say this value, since we know our base case is 1, since we know we're decrementing, let's just say like a number close to 1, but not too close, like so we can see more recursive calls. Like let's say 3. In this case, first thing that is done is we're gonna push RBP, which is 16 by the way. Or sorry, negative 16. This would be the RBP of the first function call. Right now, we're in the frame of the second function call, but we're saving the old frame pointer from the first function call. Right? And we wrote it right here. That's why I said it's good to keep track of registers. Update them accordingly. Okay? That's this. Now our RSP is here. So you can kind of see like how like we have like right here we have our callee function and our caller function here, you know what I mean? And I'll just give you guys a little illustration that this makes sense. So look at this. Right? This is our old frame pointer right here. And this is probably from your slides, but I just got it from Google, but it's basically the same thing. Old frame pointer. This is the old frame pointer. RVP is the frame pointer, right? This is the old frame, old meaning from the first function call, right? From the caller, right? The caller, which is the first function call, calls the callee, which is the second function call. And the frame pointer is pointing here, right? Okay. Let's get rid of this. Yeah, and that makes sense. Look. Now we're going to move RSP into RVP. So now, RVP is negative 48. And just like our illustration, it was like this, right? Negative 48. Okay, now I hope you're starting to connect the dots. Yeah. Sorry, I'm a little lost. Kind of got confused what I was doing. Okay, so yeah, so right now, we're right here. We just did this. We just did that. Okay, now we're gonna subtract 10 from RSP. Sorry, 16 technically. So negative 56. Then we'll do negative 64 here. Okay. So now RSP is here. Similarly, we'll do the same logic right here. So now RDI, the second, in this case, this is the second time we called this mystery 2 function. It's going to equal 2, right? Why is it equal to 2? Because I said it was 3 earlier. That was like our input. So now it's going to be 2 because remember, this logic right here. We subtracted it. We took it, put it into REX, put it into RDI. But remember, this value is subtracted by 1. Okay. So now we're here. We check, okay, it takes a jump. Why? Because it's not equal to 1. This value is not equal to 1. So we're going to take the jump because it's not equal. Jump not equals. We're going to move this into REX. Do the same thing. You can kind of see the pattern. Subtract 1. Okay. Then we call Q. Okay, first thing call Q does. Go over it one more time. Push the return address. What's the return address? Same thing. You'll see that's a pattern for recursion. The return address is like the same because, you know, yeah. Then that means we're back up here again. One more time. What the heck? I don't know how to get rid of it. Oh, sorry. Okay. We're back here. We're going to push RVP. What is RVP this time? Negative 48. In this case, it's the second function call. Second function call is frame pointer, right? Now RSP is here. from 2 pushes. It was here, and then the push made it could go here, and now it's here. Right, now we're gonna move RSP and RVP. So now RVP, I'm gonna do it just like that picture earlier. It's now negative 80. Put the picture one more time. As you can see, old frame pointer. In this case, the old frame pointer is the caller function. The second function call called the third function call. This is the frame pointer of the third function call. That's pointing to this, and where this and this is being stored. The second frame pointer. Okay. SP is RSP, by the way. Okay. Let's go back. Yeah. So now, yeah. RDI is equal to 1 in this case. So we don't take this jump. We're going to move 1 into EAX. And like how I explained earlier, right? We have our leave queue, which does what? Moves RVP into RSP and pops RVP. Okay, so first of all, EAX is now 1. Keep that in mind. We can write it down. I'm not going to write it down though. We're going to do our leave queue. What does leave queue do? Okay, it's going to move RVP into RSP. In this case, RVP is negative 80. RSP is actually still negative 80. Sorry, no, it's not. Remember, I forgot about doing this. I got a little too hasty. Okay. Negative 88. RSP is now here. Because then after that, ruler out of the way. Okay. Then we did this, this, and we saw that it was actually equal, so we didn't take this jump, right? Because, sorry, I skipped a lot of steps. This is the third time. In this case, it's equal to 1, right? Okay, so now we compare that. We're comparing 1 with this, which is right here. Since it is equal, we're not going to take this jump because this is for the jump not equal. Moving 1 to REX, and then we're calling leave queue. Okay, yes. What does leave queue do? One more time. It moves REP into RSP. What is REP? REP is negative 80. So now RSP is back here. We're going to pop REP, right? That means we're putting this value into REP, right? Because RSP is here. And what does pop do? Pop's value at RSP, which is right here, into register. The register specifies REP. So we're putting, this is now our new REP value. And then, yeah. So now, after that, our RSP is back here. Our RSP is back here. And then we have return queue. Our RSP is back here, and we have return queue. What does that mean? What does return queue do? Return queue, let's see where I put it. I didn't put it anywhere, but return queue takes the value of RSP, puts it into RIP. Let me write that down. Return queue, I'll write it right here. Number 1, put RSP pops RSP into RIP. Okay, perfect. So as we just said, RSP at this point is back here, and REP has its old stack, has its old thing, right, which makes it right here. And now RIP has this, and now RSP is back here. So what did we just do? We were in the third frame, the third function frame, the callee of function 2, right? Function 2 was the callee that had this callee frame of function 3. And now this leave queue allowed us to go back to function 2's frame. Makes sense? RSP is here. This is function 2's frame. Function 2's frame ends here. And now we're back. And now we're back. Now, because now we're pointing at here. The RBP value is pointing here. Perfect. Same logic. but now we have this RAX value of 1, right? So now we're back here. We're gonna move EAX into EDX. What does that mean? So what was EAX? Well, we just had EAX because we moved 1 to EAX and then we did all that thing. So EAX has 1 and we're moving to EDX. So that means we're taking this and then, okay, now we're moving this value. In this case, REP is now here, right? Right? So now -8 right here is that. Okay? Let me write that. Let me write that. I think it's a lot easier if I write it. REP is here. Now RSP is here. Okay? And this is pretty much gone, right? It's like the same logic how like once you call a function you go out of that scope, like it's just gone, right? That's like it's literally called stack. Okay. So now yeah. So now since our return address we popped it, so now our RIP is here 4012D1. So now we're gonna move REX, which in this case has 1, to EDX. Let me write that. RDX has 1 because EDX had 1. Okay, now we're looking at this value right here, which is this value right here. Why is this value? Because REP is here and -8 is right here. And we're going to place into REX. So now REX has what? 2. We're going to multiply them together. 2 times 1 is what? 2. Leave Q. Return Q. So that means we just, from this callee, right? Right, this callee that called this function, mystery2, just return 2. That just returned 2. Okay, now we do the same thing. We leave Q, which moves, let's use a different color. Moves RBP here. Now RSP is here. And by doing that, we have this as our current address. Keep in mind, REX right now is 2. I should have wrote earlier REX over here was 1. Actually, I write it in red just to keep coherence. Okay, so RX is now 2. RSP is, okay, so, sorry. Now we are where? Here, right? D1. So we're going to move REX, which was 2, into EDX. So now RDX is equal to 2. Now this value right here is this value right here. We move it to RDX. So RDX is now 3. Okay? Multiply them together. 2 times 3 is what? 2 times 3 is 6. And then we're gonna then leave Q and return Q. So what does that do? Well, basically now our new RSP will be here. Our new REP will be wherever it points to in terms of the main function. I don't know, maybe we had a lot more stuff. And our return address is here, which is here. Perfect. So now we're executing this, and our value is 6 right here. But this 6 is not the same as 18. But obviously, yeah, because we just chose a random input that was outside of our base case. So, but what pattern did we notice, right? If you notice, right, we were doing for 3, right? We did 3 times mystery 2, which mystery 2 was 2 times mystery 1, and mystery 1 was just 1. So it's basically like, is that not what factorial is? And you might be thinking, what was the base case for 0? It's because this factorial function was written wrong. Should have had base case of 0, but it doesn't. So if you write 0, you're kind of, I don't know. I think you'll probably have a overflow. Okay, anyways. Yeah, if you write actually 0 or any negative number, you're just going to have overflow. Stack overflow, because infinite recursion. Okay, so what value when calling factorial will be 0x18? Wait, that's impossible. What factorial number is equal to 18? Well, remember, this is hex, right? So 0x18 is actually 24. And 4 factorial is actually 24 because... yeah, okay. And that's pretty much it. Yeah, hope this helps. Yeah, hope this helps. And it's really important to know all these rules. And these are some general tips. Yep. Always draw the stack. Very, very important to always draw the stack. And I'll give you this picture one more time.